All right. So which ones do we need to maybe look at?
5.
5.
5. 9 and 11.
Okay, so let's look at number 5.
Yeah. Take a nap.
All right, so if you look at number 5, look at number 5, where is the graph increasing for number 5? All right. Decreasing is from 0 to 4 and 4 to infinity. All right. What does that mean when we draw the derivative? What should we see? Okay, so above the x-axis would be from negative infinity to negative 4, and from negative 4 to 0. And below the x-axis would be from 0 to 4 and 4 to infinity. All right, what else can we see from the original? We have a maximum, right? Where's the maximum at?
I thought there wasn't.
Is that arrow
Or the middle one count?
The middle one has a max.
Oh, 0.
Yeah, 0. Okay.
I was really thinking about that, but I was like, no, that doesn't make sense.
Yeah, no, there's a
It doesn't
maximum.
even look like it reached it.
Oh, it's a
the
relative
ones
max.
that don't.
Yeah, it's a relative max. It's not an absolute max, but there's definitely a high point, right? Okay. If that's a max for that point, then what does that mean for the derivative? It's an x-intercept.
Wait, so isn't there a max for that right part too? Like,
This part, it's showing, this is, your calculator does this too. It's getting close enough to the asymptote that the computer had a hard time graphing it.
oh, so it's supposed to really continue.
It's supposed to continue, yeah. All right. What about concave up, concave down? We could describe that. So negative infinity to negative 4, and 4 to infinity. And where is it concave down? Negative 4 to 4. And what does concave up and concave down tell you about the derivative? Yeah, it tells you where it's increasing and it tells you where it's decreasing. So the derivative is going to be increasing from negative infinity to negative 4 and 4 to infinity, and it's going to be decreasing from negative 4 to 4. Okay. So when I looked at this, I knew there was going to be an x-intercept of 0. And then what do you think is a valid conclusion about negative 4 and positive 4? Like those actual values, negative 4, positive 4. They're asymptotes in the original function. Does it appear like they might be asymptotes in the derivative as well? Yeah, our information seems to support that. Those values seem to get skipped. So I'm going to go ahead and draw some asymptotes in there. And don't forget that you guys, you know how to find derivatives by hand, and so there's a certain amount of this that kind of is going to make sense. So if we think about what type of function would have given us asymptotes, think about it. Where do you normally, what functions
We
normally
need
have
Leslie
asymptotes?
to sign out, please.
All right.
But
Okay.
So what type of function normally has asymptotes? Piecewise and? The fraction one, right? And what would be on the bottom of the fraction that would give you an asymptote of positive 4 and negative 4? X minus 4x plus 4, right? So is it okay if I write x squared minus 16 on the bottom? Right? think about, this is a fraction, right? So think about how would you have taken the derivative of this if you'd done it by hand? Quotient rule, right? And you normally when you do the quotient rule, you end up with the bottom squared, right? So would it make sense that our original had x squared minus 16 and our derivative had x squared minus 16 squared? Right? I don't know for sure what the equation was, but this likely happened. So would it make sense the asymptotes are going to be in the same spot? It totally makes sense, okay? So when you're doing these problems, you can use a little bit of what you know about derivatives to help you think of the problem, okay? And a few times when I was drawing the derivatives, that's kind of what helped me know what shape it needed to be, all right? And I'll reference that on a few other questions that we could do. So if you look at this one, we know we have to be above the x-axis from -4 to 4. We know it's not going to touch the x-axis at all, right? Because we already know what our x-intercept is, so we know we can't touch it. And then we know that from -4 to 4, it's also increasing. So how can I draw something above the x-axis that's also increasing, that does not touch the x-axis? What should that look like? Yeah, it's going to be a very similar shape to this one, right? Yeah, so it's going to get closer to the x-axis. It can't cross it because then it wouldn't be considered increasing, or it wouldn't be above the x-axis anymore. And we know the derivative has to be slanted upward because we know that the derivative is increasing right there. Okay. All right. Now we know that the derivative is also above the x-axis from -4 to 0, and this time it should be decreasing. So how do I draw something above the x-axis that is also decreasing? It's going to be this. It's going to be like this again? No.
Like the other way.
The other way. Okay. So the other thing that can kind of help us is we know how asymptotes work, right? The curve gets close to them. So we should see this is how the decreasing would work. The curve's going to get really close to that asymptote right there, right? Okay. All right, and then we know that the graph is below the x-axis from 0 to 4. And we know that from 0 to 4, it should still be decreasing, right? Because this says the graph is decreasing from -4 to 4. So in between these two asymptotes, it has to be decreasing the entire time. So it's going to go down, and then it's going to follow the asymptote, because that's what these graphs do. They follow the asymptote. All right. And then let's go ahead and do the last part. The last part says from 4 to infinity, and that part is below the x-axis. And then it has to be increasing, and so it must look like this. This, on the worksheet generator, this was a hard question. So yeah, so I expected us to struggle. Yeah, that was my expectation. Okay, let's look back at number 4. Okay. Because we can use what we know about derivatives to answer number 4. So does anyone know what type of equation number 4 must have been? So it has to be an x to the third. Why does it have to be an x to the third? Yeah, if you look, it has it has a max and a min. So usually your exponent is 1 more than however many times it turns around. The other thing I notice is it has 1, 2, 3 x-intercepts, and your x-intercepts, if it goes straight through, you can count those, and it tells you the degree of your function. So this is an x to the third. I don't know what numbers go with it, but I know somewhere in the problem the highest coefficient or the highest exponent would be a 3. And so what would you expect to see for your derivative?
X squared.
I would expect to see an x squared. I don't know what the other numbers are, but my derivative should be a parabola. Does that make sense? I'm thinking about what I know about derivatives to draw it.
It's not 5 factors.
All right, so let's look at the other things that we know. So for the original function, where is the function increasing? -1 to 0.5. I'll go with that. I think actually, doesn't it look like it crosses at 0.5? I think that it might be a little bit less than 0.5.
Yeah, I think it's 0.25.
0.25? Okay. Whoa, James. 3 nice things about yourself. Foul. Three nice things. Ready?
About yourself? Myself is 2.
Yeah, but it's 3 in this room.
Oh.
Oh.
That's right.
I'm not failing this class.
Oh.
Very good.
Boy.
Oh, that's not
That's a compliment. That is a compliment.
Don't say there's nothing else, because then you're gonna have to do 5, because you're gonna have to add another 3.
I talked to the USC baseball coach the other day.
Oh, yeah.
There you go. There you go.
Oh, USCG.
That's not really a good thing about yourself, though.
USCG, yeah, it is.
That means they want. That means
Okay, he's a good baseball player. That's what he meant to say.
Yeah. And then I am very glad that I am on the National Honor Society.
There you go. He's on it. He's smart. He's on the National Honor Society. So that negates his previous statement. There we go. There we go. There we go. All right. So it's increasing from -1 to 0.25. And then what else do we have? We've got decreasing, and what should we say for that? Negative infinity to -1, and then where else is it decreasing? Yeah, 0.25 to infinity, right? And so what do those things tell us about the derivative? So it's above x from -1 to 0.25. It's below x from negative infinity to -1 and from 0.25 to infinity. Oh. Well, we just made you say nice things about yourself anyway. I do care. I do care. All right. And then we have maxes and mins. Why am I calling it extrema? Why am I not specifying? It doesn't matter. The y doesn't matter, right? All right. So what are the x values where the extrema are located? -1
Not 0.5, it's 0.25.
and 0.25.
Oh, okay.
And so, since those are extrema, where do we expect to see those on the derivative? X-intercepts. All right. And we can also do our concave up and concave down. These are going to be somewhat approximate, right? Because those are kind of hard to tell. So, concave up, somewhere in the middle-ish of that. Okay, so what do we want to say for actually, it kind of looks like, it's almost like you could,
Looks like -0.5.
yeah, I was going to say, I think you could do it right there. So we'll say it's concave up from negative infinity to -0.5. And then concave down from -0.5 to infinity. And what does that tell us about our derivative? So it's increasing from negative infinity to -0.5, and it is decreasing from -0.5 to infinity. Okay. Did everyone already draw this one?
Yes.
A lot of us
Looks
did?
like a little ghost.
A little ghost, like an upside down parabola that's also a ghost. We can I like that Halloween theme you've got going there. Yeah, there we go. So x-intercept at -1 and at 1/4. And then what should I do in between those points? So in between those points, we should be above the x-axis. So it goes up, bloop. Now, you could do a little bloop if you wanted. I did a little bloop. If you wanted to be crazy and have yours go like this, you totally can. Because we have no y values here. You can make it as stretched out as you want. I did a little bloop because it's easier to draw. All right, and then the other parts are below the x-axis. And there's our parabola shape. And then here is Lauren's ghost.
Yay!
And the ghost is happy.
Oh, cute.
Yeah.
That's an ugly ghost.
You can look at the point of inflection, but I found it didn't necessarily help me when I drew it. I mean, so when I looked at it, yeah, the point of inflection, I guess, would be that high point, and you can kind of check that when you look at the increasing and decreasing. So the point of inflection is kind of built into the problem.
Yeah, I can see that now.
I don't know if it helps a ton either way. All right.
Emma thinks it looks like a grave.
Okay, we're going to go over number 7.
This might actually be
That's okay.
That's just
You're good. We're gonna think about it. It's not a bad idea to think about these. So, all right, we are gonna talk through number 7, and then I'm gonna maybe give you guys a few minutes after that because the other difficult problems were 10 and 11, and to be honest, I haven't tried those yet. So I want you guys to spend a few minutes working on it, and then I'll go over 11. Okay? Yes, ma'am.
Sure, you got a lot of people.
You might have gotten my answer or my master copy because I lost it. So I think, did somebody get the second page? Nope, just the first page. That was my bad. There's a second page. If you look in the back by the window, it's somewhere back there. Yeah, this is a straight line, but the derivative or the original function is not going to be a straight line. So the derivative, yeah, the derivative has just a plain old x, right? Yeah. So that means the original function. All right. Wait, I think some of the people who might need to hear this are not hearing this though. So the derivative had an x all by itself, and if we think about, are you listening, Flora? Are you listening? If we think about how original functions work, when you find the derivative, this must have been an x squared. Why must this have been an x squared to take a derivative and get it to an x? Yeah, it's the only way for it to have an exponent of 1 is if it used to have an exponent of 2. Yeah. So that means that your function for this one must be a parabola. You're going to have a parabola somewhere here.
All it does is touch -1.
Yeah. So when you look at this one, where is it above the x-axis?
Negative infinity to -1.
Negative infinity to -1. What does that mean for the original function? Increasing from negative infinity to -1. All right. Where is it below the x-axis? It is below the x-axis from -1 to infinity. And so what does that mean for the original? It must have been decreasing. It has an x-intercept at x equals -1. What does that mean for the original problem? It was a max or a min. Can we tell which one it is? It switched from above the x-axis to below the x-axis at that point. That's a min. No. It's a max because it was increasing and then decreasing. So it was a max. We got a max at x equals -1. And this graph is slanted down. This graph is decreasing the entire time. So what does that tell us about our original? It's concave down. All right. So we have a maximum at -1. Do you guys want to put your maximum like up here? Do you want to put it down here? Do you want to put it in the middle? Let's put it at 4. That's what I heard. Okay, maximum at 4. So we got the the x coordinate of the maximum has to be -1. The y coordinate can be whatever you want for it to be. And then we have to have the graph increasing up until that point at -1 and then decreasing after that point at -1. And we were concave down the whole time, so we got it.
Oh, dang, that's, wow.
All right, so what did you guys say about number 10? What information did you notice? So the original function is going to be increasing where this is above the x-axis, right? So it's above the x-axis from negative infinity to 0. So since the derivative is above the x-axis, then that means our function should be increasing. The derivative is below the x-axis, so we should be decreasing from 0 to infinity. The derivative has an x-intercept, so we're going to have an extrema. And can you tell if it's a max or a min?
It's a max because it goes from
increasing. It goes from increasing to decreasing, so it's going up and then coming down. So this is a maximum at x equals 0. And then the derivative is increasing from negative infinity to here-ish. So we are going to say that we are concave up from negative infinity to, and what did you guys call that number? 0.75? Okay, so this is negative 0.75. Yeah, it can't be 1, it's not right on the line.
relative.
I mean, it's got to be some sort of decimal. And then it's concave down because the derivative is decreasing for a little portion. And what would the concave down part be? Concave down. Okay. And then it is concave up, so this graph is increasing, so that means for us it's concave up from 0.75 to infinity. Okay. So our maximum has to happen at x equals 0. What y value do you want it to have there?
4.
4. We really like that number. All right. Can you see that? Now, it has to increase from negative infinity to 0 and then decrease from 0 to infinity, right? And so we know that on either side it's going to go down. We know that, right? And we have to be careful to look for the concave up and the concave down. So when I drew this, I was like, well, the concave down part is the weird little part there, right? Like right in the middle, it's going to be concave down. So what I did is I just drew like a little U shape and I made a little concave down right here. And then, what do you have to do on either side of this? You have to make sure that this part switches to concave up. So this has got to come out like that. And this has got to come out like that. And your graph could be shorter than mine. Your graph could be taller than mine. Your graph could be shifted up and down at all because we don't have any y values here. So it's up to you how the rest of your graph works. Okay?
Wait, can't go under the x-axis?
Yeah. It doesn't matter. Because these things never said anything about y values. It doesn't matter because this is the original function, not the derivative. All right, let's look at this one. All right. So our graph, are we ready? Our graph is above the x-axis, so it is increasing. It is above the x-axis for what values? So 0 to 2 and 2 to infinity. It is below the x-axis, so it's decreasing from and negative 2 to 0. It has an x-intercept at 0, and what is that on our graph? It goes from decreasing to increasing. It goes from decreasing to increasing, so that's a minimum at x equals 0. And then we want to look at where the graph is increasing and decreasing to see where it's concave up and concave down. So this part of the graph is decreasing, so what does that mean? Concave down for our original function. So from negative infinity to negative 2, it's concave down. From negative 2 to positive 2, this is increasing. So what does that mean about our graph? Concave up from negative 2 to 2. And then here the graph is decreasing. So what does that mean about our original function? Concave down. So union 2 to infinity. Okay. So based on this information, what appears to happen? What types of interesting things are happening at negative 2 and positive 2? It appears to have an asymptote there, right? And that would make sense based on how we know that derivatives interact with their original function and how asymptotes are made. It's kind of a logical thing to have happened here.
Yes, very good.
We have a minimum where x equals 0. What y coordinate do you guys want your minimum to have? 0. Okay, so we can put it right there in the middle of the graph. And since it has a minimum there, what should it look like? Should look like a parabola, right? Right there in the middle. Yep. And it's got to be concave up, right? Negative 2 to 2 says concave up, and so that's a U shape, and that fits. Everything about that we have written down fits our graph looking like this, right?
The negative 2 to 2 though, like doesn't have to be something.
Concave up. It's just got to be a U shape going up.
But there's also concave down inside the negative 2.
No, concave down is on the left side.
What I'm saying on the graph.
On this, it's not concave down.
Oh, from negative 2 to 0.
From negative 2 to 0, it is slanted up. That's an increasing. The derivative is increasing, so that means concave up. So you have to interpret what it means and not necessarily look at it as like the picture of what it should look like, right? And we interpreted what it meant. We said negative 2 to 0 was increasing, and so the interpretation of that is that it was concave up. Yeah. So that it messes with our brains. It's part of why I'm moving this off to the side so we can't really see the picture, because the picture is not actually helpful for when you draw it. Yeah. All right, so we got concave up. That works. We are decreasing from -2 to 0 and then increasing from 0 to 2, so that fits our information completely. So now we need to do the stuff on the left, and we are noticing that from -infinity to -2, the graph has to decrease, and it has to be concave down. So what should it look like? So it should kind of look like that, yeah. Yeah, like an exponential graph going down. That's good. Now, I drew it right here because it could have been anywhere, technically. I drew it right here because we often see horizontal asymptotes that kind of make it look like that. But you could have drawn it up here and you would have been equally accurate. You could have drawn it all the way down here, you would still have been accurate. So based off the information, that curve can move up and down. All right. And then last, we have to do our increasing from 2 to infinity, and we are concave down from 2 to infinity. So what should I draw with that?
You should draw it like this.
So like the same thing, just on the other side.
Yeah.
James, I always appreciate you, buddy.